All right. So, okay. So these are the results, and what I want to show you is, if you remember, we said that we started something which is quote unquote impossible. We changed it to something which is quote unquote possible, and so you might buy that this is the right thing to do. We believe that this is looking at your estimate based on the equating things based on the number of times they appeared is the right thing to do. The other thing is just lost. The other information, the difference was lost, and you're trying to overfit the data or overfit more than overfit the data. If you try to guess if you try to break symmetry between things that are symmetric. So we think it's the right thing to do, but we can also ask the question that we mentioned before, does this variation help us with the original problem, trying to estimate the probability of individual elements? Does it help us? So we'll show that it does. Why did we have this boundary before? Thanks. Okay, so does it help us with the real data, not with the total probabilities? So we know that for the original data, there's nothing we can do. It will be infinite in the worst case and so on. But here's an experiment. So we took a Zipf distribution. Zipf distribution is a very common distribution in nature. It behaves like 1 over a polynomial. So in this case, we looked at something that's proportional to 1 over I going from 1 up to 100. And we look at the L1 distance, or error, L1 error, average over 100 runs. And so here it's shown this is the number of samples n that you take, and this is the L1 distance, called error here. And so, and notice the L1 distance can go up to 2, because the summation of absolute value of differences, it can be, like if you have 1, 0, and 0, 1, it's 2. So the L1 distance for empirical frequency goes down like this, and take some variation of good Turing, it goes down like that. Eventually, they'll converge to the same thing, because both of them, as David mentioned yesterday, both of them are consistent. So if you have enough samples, they'll both be good. But the issue is that when you have few samples, this variation of good Turing does better. Okay. So this is now for the real data, not looking at this total probability. This is going back to the real data and saying, did we estimate the probability better or worse? Any questions? Okay. So this is an example where once you convert it to the possible, also helps you do something better with the impossible.
I think you have a better estimate.
Right. So, like we can view our estimate as a variation of good Turing. I mean, it's all kind of like the
red line is not your estimate.
It's one of the variations of the. It's one of the variations. The reason we use this one is the more sophisticated you want to get, the larger the number of samples that you need for it to kick in. So. So if, like here, we're looking up to 450 samples. It's maybe not enough to get what we're looking at. Okay. So now we came to the moment. This is like the moment of every talk, the moment that everyone is waiting for. Like for Rudiger, it's the moment that the talk ends. So, right. Right. But for dedicated people like Professor Che, so it's the moment of right, the moment of truth, right? Is that what I said? Yeah. Moment of truth? Very close. It's the moment of proof. That's the moment everyone is anxiously waiting for. Yeah, exactly. So truth about truth. So proof, like David's saying, proof is showing that that something is showing the truth, right? That's what proof is about. So we have to be a little honest. It's not true that. Truth is that's the moment of proof is not the moment that everyone is waiting for. Not everyone is waiting for that. So the moment for proof for many people is the moment of, I don't know, catching up with sleep that they were missing last night, or other people is catching up with email or catching up with friends and so on, right? So, and so on. So I'm sure that people could give us more. What do people here do when they hear a proof? Any suggestions? They, sorry? They solve it.
They go to the bathroom.
Oh, the bathroom. Okay. Right. Yeah. 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 We should stop here. Okay. So so this is actually particularly true here because good Turing it can get a little complicated. So here is an example of a title of a paper that later became a monograph about good Turing.
Is Gary Shapley there?
Yeah, it's from Bell Labs. I think so. So the proofs are complicated. Like I said, the technique was invented in World War II. It's only in 2000 people started being able to prove things about them. And the original proof, McAllister and Shapiro, was fairly complicated. But I think the results are somewhat unlikely, like what I told you now. Like maybe some people said it is weird or maybe not even believable. So maybe show you a little bit of the proof, just you see, get the idea, and look more. Okay. So maybe some proof is in order. Like I said, the original proof was fairly complicated because of all kinds of assumptions and things that don't quite match in the original formulation. So we'll show you like a way you can modify the formulation. It's still proving the same thing. That simplifies it a lot. So I think actually the way we see it now, I think probably one of the simplest proofs. And I'll show you maybe half of it now. I was planning to give 2 different talks, and so I didn't think of that time, but otherwise we could have even shown more. Okay. So one part that helps us simplify the proof is what's called Poisson sampling. So I'll just mention that. So P, remember that's what we have. We have a distribution over some alphabet X. And what we'll show now is we'll show that good Turing is an unbiased estimator. And a little more. Okay. So that's as much as we'll show now, and the rest is actually not much more complicated. P is a distribution over some alphabet X, and Px is the probability of X. Okay. And we want to show that good Turing is actually an unbiased estimator. So that's a good part of it. Shows you that it's the right thing to look at. The question will be like the variance. Maybe you can believe it's not high. And so what normally we look at is you take n samples. That's the way we describe it. You say, hey, you have n samples. What can you get? Okay. And so if you do that, what you do is you take P and you sample independently from P n times. And you can let mx be the number of times that x appears. So for example, if the sequence is heads, heads, tails, then m heads is 2, heads, heads, tails, and m tails is 1, because it appeared once. So this is just the number of times x appeared. And so it's easy to see that mx is distributed binomial with parameters n and px, right? Let's say heads has probability of heads, right? And you took n samples, it will be binomial n samples with the probability of heads. Okay. And the problem is that these mx's are dependent. And why? Because, for example, they add to n, right? The number of heads plus the number of tails adds to n. So they're clearly dependent. So one way to get around this, so that complicates, that's one of the complications here, that you have dependencies and you have to deal with them. Another one is that when you do it, numbers don't work out exactly right, and that's what complicates previous proofs. So one way to get around this is what's called Poisson sampling. And so here's the Poisson distribution with parameter lambda. It's e to the whatever it is.
Is it okay if we go to the cinema version?
Sure. So now we have a proof in dark room.
Is it okay? I think so.
Okay. All right, so here's the Poisson distribution parameter lambda, and what we do is, instead of selecting, let's say n is 1,000, instead of selecting always 1,000 samples, first we're going to select a random length, which is distributed Poisson with parameter 1,000 or n, and then we select that many, and then we select from P sample P independently that many times. Is that clear to everyone? So if I want, initially, if I want to take 1,000 samples, initially I took 1,000 independent samples. Here I'll take a number. It could be either 0 or it could be almost infinity. I first look at a number which is Poisson 1,000. That number is closely distributed around 1,000. It's probably plus minus square root. The standard deviation is square root of 1,033, so it's between 970 and 1,030. It's very close to there, but could be anything. And I sample independently that many times. And the nice things about this sampling is, first of all, if you look at mx, the number of times that x appeared, it's now going to be distributed Poisson with parameter n times px, which is not so surprising. If you believe it's Poisson, that should be it, right? So it's going to be, instead of binomial, it's Poisson. It's a little nicer to analyze. Okay. And then the number of times that different symbols appear is now independent of each other. So if heads appeared 3 times, it doesn't tell you anything about how many times tails appeared. So you get independence, which simplify things. And you can also show that if condition on n equals n, or actually you can do it for any other number, then the number of times x appears is distributed again binomial with n and px, just like before. Okay. All right. And then again, if you want problems for people to think of, maybe that's one thing that they can look at. And again, Pn concentrates around mean n, and therefore, whatever results you get for the Poisson sampling, they'll be very closely related to the results you'll get for fixed n sampling. So it's just easier to prove, and the results translate very easily. Okay, so is that okay? Okay, so maybe a few definitions. So just we have one slide of definition and one slide of proof. So NT, we defined it before, is the number of elements that appeared t times. And if we let the indicator function 1t of x be 1 if x appeared t times and 0 otherwise. Okay. So 1t of x if x appeared t times, this number is 1, and otherwise it's 0. So this number is not a random variable. For every x and every t is a random variable. So it's a 0, 1 or Bernoulli random variable. Then we can express nt as the summation of this indicator function. It's summation over all x. Nt is the number of elements that appear t times. We can sum over all x and add 1 if x appeared t times. Okay, so it's that. Okay. So we can express nt as a summation of these Bernoulli random variables. And notice that these random variables, each one of those is a random variable, and they're independent because we're doing a Poisson. Okay. And the other quantity that we looked at was the total probability of elements that appear t times. That's the quantity that we're interested in estimating. Okay. That property can also be expressed in a sum like this. Is just the summation over all x's. And then instead of just looking at the indicator function, we need to multiply by the probability. So we sum over all x's that appear t times. We sum the probability. So that's the total probability of things that appear t times. Okay. So you can see that we can express both of them in a very, very similar way as a summation of Bernoulli random variables that are independent, and maybe in this case they get multiplied by some constant px. Okay. And what we can observe are the NT. That's the sample that we're given. And what we want to do is we want to relate it to these numbers. So we're given these numbers, we want to relate to that. That's the only question, right? Right? Because we observe all the information we have are the NTs. We see how many elements appeared once, how many elements appeared twice, and so on. That's all the information we have. Anything else is useless. Right? I mean, the only other information is we know the names, what appeared once, what appeared twice. That doesn't matter to us. So all the information we have is how many elements appeared once, N1, N2, N3. Maybe we have N0. And what we want to do is to estimate T0, T1, T2, and so on. Okay? So, so it will be useful for us to define a slight variation of this. So instead of summation, the sum of the probabilities of things that appear t times, we can also look at the sum of the probability raised to some power r. Okay, so the sum of the square of the probabilities of things that appeared once, the sum of the squares of the probabilities of things that appeared twice, and so on. So we denoted TTR is the summation of all things that appeared t times of their probability raised to the rth power. Okay, so if we look at r equals 1, we get back to this thing, but we can look at the summation of the squares of the probabilities and so on. Okay, and so one thing to note is that each of those three quantities, nt, the number of things that appear t times, the tts, the total probability of things that appear t times, and the total probabilities squared, let's say, they're all sums of Bernoulli random variables, right? These are Bernoulli random variables. In some cases, they're scaled by some constant, okay? And so it's very simple. And the other thing is that because we're looking at Poisson, then each of those terms in the sum are independent, right? Because if x appeared 5 times, it does not affect the probability that y will appear 5 times. So it's a very simple case. Okay. So let's show that the good Turing estimator is unbiased. Yes. Yes.
So, are you assuming all the PX?
No. Why do you think we're assuming?
Because you are fixing the T. Have T's and all the PX.
No. The PX be anything. If you want to think of English, okay, X could be the word, cat, or the word dog, and so on. So those are the probabilities. And now we took a sample, and I'm looking at t equals 3. I'm looking at all the words that appeared 3 times. So there may be like 100 words that appeared 3 times. So nt is going to, n3 will, in that case, is going to be 100. It's summation of the indicator function of things. Correct.
And then for all the things that appear 3 times, they should have the same probability.
No. No.
That's a, the one is a natural estimator. This is the underlying probability.
These are the underlying. Correct. This is the true probabilities. Right. And in fact, we're not even going to say they have the same probability. We're just going to give the total probability to all of them. We're not going to, if you want, you can divide by 3. We'll tell you the total probability is like 0.1. If you want, you can say each one is probability 0.1 divided by 3, but we'll just tell you it's equivalent. So we're not going to even bother dividing by 3.
So the sum of scared Bernoulli random variables in that independent.
These
Independent across x, right?
correct. So when you look at the different x, they're independent. Correct. 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 So the fact that heads appeared 5 times does not change the probability that tails will appear 7 times. So, okay.
So to get back to the result for fix A, you have the condition.
So okay. So let me give you like a simple answer. The complete answer is slightly more complicated than this. Like we said, Poisson. Actually, I think it says no, it doesn't. Okay. So Poisson concentrates. The standard deviation is square root of n. Right? So if n is 1,000, Poisson is going to be somewhere between, like we said, 1,000 plus minus 30 or something like that. 33. Okay. So and remember, we don't care about constants. We're not telling you what constant in front of the 1 over delta square or delta 1 over delta to the 4 and so on. So let's say that you want to do something for size 1,000, let's say, for fixed n. Then what we'll do is apply our results, instead of size 1,000, apply our results to maybe 900, okay? And select Poisson 900 with very high probability, because you have 1,000 samples. With very high probability, the number Poisson will give you something less than 1,000, and then our result will apply. If in the first step, when you selected the Poisson, you got 1,010, you just that adds to the error probability, which is very small, but it's exponentially small. Okay, so like I said, to do the thing, you need to do a little more. Okay, all right. Okay. Okay, so just to show that it's unbiased, or okay. Okay, so oh yeah, we could do that. So, but maybe just to show you, because it is actually simple. So maybe just go over it. And should we or not? R, remember we're looking at the rth power. We're looking at p to the r. Oh yeah, it's defined here. It's the falling power. So, I mean, one nice thing is it shows you like the simplicity of this problem. So this is just, like I said, this is half of the proof. And this is a problem that people could not solve. We did not solve the good Turing, right? I mean, it was McAllister and Shapiro that deserve a lot of credit, but their proof was a lot more complicated. But just want to show that with the techniques that we have now, you can prove this thing very simply. And this, like I said, is half the proof. So if you want, we can go over it quickly, or if not, so this will show you that good Turing is an unbiased estimator.
So this idea of total probability estimation already appears.
So, right. So you can say that it goes back to good in Turing. Okay. And what McAllister and Shapiro showed was that if you look at up to something which is less than square root of n, then each one converges. Like individually they converge. What Druk and Mansour showed that if you want to go beyond that, then you can just combine with empirical frequency and you look at the range where each one of them work, and the ranges, you take the union of the ranges, that's everything. So that's what they showed. And then if you want to get it to the L1 distance, or KL divergence, you need to do a little more work from what they have done. And then if you want to improve it, you need to do a little more work. Right. Okay. I don't know that they've looked at it, like to say that, you know, if connected to, like if you try to estimate the distribution of real things, you cannot, and so on. But the looking at these probabilities, that goes back to good in Turing. Right. Okay. So, what is the expected? So remember that this is what we're trying to estimate. We'll try to eventually estimate it. Just we only care about r equals 1, but we're doing it a little more generally here. So you try to estimate the total probability of things that appear t times. And so here we're looking at the summation, which is the summation of those probabilities, and here we're looking raised to the r. So this is what we've said. We had this formula before. It's the expected value of summation of x appearing t times, and then multiplying by its probability raised to the r. That's a quantity we don't know. We try to estimate. Okay, not the expectation, but the actual probability. Okay, so by linearity of expectation, it's summation of p times the expected value. Now, this indicated function is just a Bernoulli variable. So its expectation is the probability that it's 1. So in other words, this expectation is the probability that x appear t times. But x is distributed, the number of times that x appears is distributed Poisson with parameter n times px. So it's the probability that if you take Poisson n times px, it will appear t times. So it's just, this is the formula for the Poisson. It's e to the minus npx times this quantity. Okay. And so now what you see is that you have px raised to the r, and you have px here. It's kind of dying to be combined. So what you want to do is you have px, you want to have px to the t plus r, and then you want to keep this form. So you multiply by n to the r, and then divide by n to the r. And here you need to have t plus r factorial like this. So you need to, here your t, so you're dividing by t plus 1, t plus 2, and so on up to t plus r. So you need to multiply by this thing here. Okay. So this is equality. Okay. So now this constant t plus r to the r divided by n to the r goes out. And what you get here is exactly, this is the probability. This is exactly the probability that if with t plus r, right, that x will appear t plus r times, right? This here is the probability that x will appear t plus r times, which is the expected value of the identity function, right? This is the probability that x will appear t plus r times, which is exactly this quantity here. So what you have is this quantity times the summation of the identity function for elements x appearing t plus 1 times is just the summation is just the number of elements that appear t plus r times. Summation of the identity function for x appearing t plus r times. It's just the number of elements that appear t plus r times. Okay, so it's just the expected value. So special case of, so we okay? So special case of this is plug in r equals 1. So what you get is the expected value of the total probability of things that appear t times is just going to be here plugging r equals 1. So it's t plus 1 raised to the 1 divided by n times this quantity here times the expected value of nt plus 1. Okay, so it's, in other words, if you look at the total probability of things appearing t times, the expected value is t plus 1 over n times the expected value of things that appeared t plus 1. But this quantity should look familiar. In fact, should look familiar from here. Should look at this. This is the same as the empirical frequency for t plus 1, right? So this is equal. So this, I put the expectation outside, so it's expected value of this, which is the expected value of ft plus 1. And this is the definition of the good Turing gives for this thing. So this is good Turing is just this quantity. So the expected value of the good Turing, so the good Turing is just ft plus 1. So the expected value of the good Turing estimator for t is the same as the expected value here. So this is the nice thing over like what McAllister and Shapiro and so on. They did not get complicated values. So they had to, number one, deal with dependencies when they move on, and they also had discrepancies. But here you just get equality and everything when you independent. You just have the sum of independent random variables, all very clean.
Does this also indicate that if you want to match higher order movements, like can you reverse engineer this to give better estimators for higher order movements?
You could probably, Yeah, we did not necessarily try, but so there's actually some amount of work now on estimating moments of a distribution, and people use various techniques for those as well. Yeah. Okay. So anyway, so this is it. So you have the good Turing estimator has the same expected value, and all you need to show is that they have that these quantities have low standard deviation. Because if they have low standard deviation, then the probability that this one will be different from its expectation is low. The probability that this one will be different from its expectation is low. Use the union bound. The probability that one of them will be different from its expectation is low, and you're done. So all you need to show is that each of those has a low variance. But because the summation, each of them is a summation of independent random variables, but Bernoulli random variable, that's very amenable to showing that they've, so you have summation of independent random variables, and you normalize them, they'll have low variance. That's all there is to show. Okay, so this is it. So hopefully it was like maybe not one moment, but maybe 2 moments. But okay. All right. Okay. So we can. Okay. So then summarize. You probably forgot, but we started by saying we're going to talk about 2 problems. One is estimating discrete distribution. The other one is estimating continuous distribution. For the discrete distribution, we said we'll talk about 3 problems. One is probability estimation, which is what we're talking about now. The second one is compression, and the third one is classification. So we're done with the first one. So for the distribution estimation, what we said is we want to estimate a distribution to some distance delta. And we said if you want to estimate individual probabilities, then for KL you need something that goes proportional with K and 1 over delta. And in the worst case, you need, if you don't have a bound on K, then you need infinitely many samples. So here I wrote it for KL divergence, but you can do the same thing for L1. But in the spirit of the art of the durable, we're saying that all natural estimators, if elements that appear the same number of times, you assign to them the same probability. So without loss of generality, just look at the total probability. And then for KL, you need some number which is 1 over delta squared. K no longer appears. So if you give me 1,000 samples, I can tell you how well you can estimate it. Okay, it doesn't matter what K, you can estimate the total probability to live with value. Okay, and this holds for any K in any distribution. So it's very uniform. It's a uniform bound. 1,000 samples. This is what you can do. This is your error, and that's it, no matter what the distribution is. I'm sorry, and this is where infinity goes to a constant. So before you needed infinitely many, and now you need a constant number, and you can show that these numbers are optimal. Okay. And the estimator is a linear time estimator, and some implications. So it's impossible to estimate the probability of individual elements because you just don't get that information. If you take a size of size 1,000 and your alphabet is English of size 500 million, there's just no way you can estimate things. So that's not something you cannot do. Okay, because for one thing is things with different probabilities can appear the same number of times. So on the other hand, if you assign the same probability to things appear the same number of times, you get the total probabilities, and they can be estimated uniformly. And equivalently, another formulation, I didn't present it that way, but you can equivalently say that you can approach the performance for any of the best natural estimator. Okay. And as the graph shows, it also helps with the original problem. It gives you a better estimate for the individual properties. And then what applications? So give me maybe 10 minutes, and we'll get to an application. Yes.
So by the L1, the L1 is equal to probability.
Correct.
So the individual probability.
I did. That was the first example that we saw. We saw the first example. It needs to grow linearly. So no matter how you're going to address it. But what this shows is even though the number, if you look at the individual probabilities, then it will have to grow with the alphabet size. Cannot have a uniform bound that if you give me n, I can tell you how well you can estimate. But if you look at specific distributions, it can give you better results, at least than empirical frequency. It's okay? Okay, we good? Any questions? So if not, then we move to compression. Okay. And compression is actually the first problem along these lines of trying to see what you can do, what you cannot do, that we worked on. And there are a number of people here that have heard this result. In particular, Professor Urbank has heard a lot about it before. So I'm going to be much more quick, much more brief about this, but hopefully give enough information so you can understand. So what is compression? You have an unknown distribution, an unknown probability P, and distribution P that's distributed over, again, alphabet size K. And then you're getting independent samples, n of them, distributed according to P, xn. And your goal is to compress the sequence using the least number of bits, right? That's the basic information theoretic problem. And so if P is known, then how many bits do you need to do that? The entropy, thank you. Then you need the expected value of log of 1 over the probability of the sequence, which is n times the expected value for individual elements, which is n times the entropy of the sequence. So that's if you know the distribution. And how do you get it? You get it by assigning to every sequence x. Roughly speaking, if a sequence has probability p, you assign it to it log of 1 over p bit. But of course, in order to assign to a sequence x log of 1 over its probability, you need to know what the probability is. So that in general is not known. So if in that case when p is unknown, then you can show that any compression algorithm is equivalent to assuming some distribution q, because any compression will tell you what you assign to every sequence. You look at the number of bits. That's going to be log of 1 over q, but Kraft's inequality, roughly it's log of 1 over q for some other q that you can back out if you want. You can calculate. So any compression algorithm will be equivalent to some q. And so the expected number of bits that q will use, that your compression algorithm will use, is the expected when x is distributed according to its real distribution. Instead of log of 1 over p, which is the length you wanted to assign, it's log of 1 over q, which is the length you are assigning. So this is if any compression algorithm that you have will be equivalent to distribution q, and your expected number of bits is the expectation, the real expectation of log of 1 over q. That's the number of bits that you are assigning. Okay. So the extra number of bits that you do, which is that you incur, the penalty that you incur because you don't know p, is the difference between this larger number, it turns out to be larger, and this, the number that you use, and the best you can do, which is the expected value of log of p over q. Okay. And so this is called the redundancy. So this is the expected, and the best number is the redundancy. It's the extra number of bits that the best compression algorithm requires for the best distribution. Are we good? And there's a lot of work on this, and very nice work. And what they do typically is they look at the per symbol redundancy, so they're normalized by the sequence length. So it's 1 over n, the minimum of a best compression algorithm, the maximum of all p in some collection of distribution of this penalty. Right, this is the penalty. And what people can show is that this redundancy is a function of n, behaves like log n over n, and then this is the number of parameters, which is k minus 1 divided by 2, not so important. But, so it's k minus 1 over 2 log n over n. So this is a very nice result because it says that as the sequence length goes to infinity, the redundancy, the number of bits that you need, the extra number of bits goes to 0, so you can compress to the entropy. Okay, but again, this is what the kind of thing we don't like. We don't like to say the k is fixed and then goes to infinity. We like to say, okay, in real life, you're given n. You're not given infinity. You're given n equals 1,000. What can you say? So you can see if k is much larger than n. For example, if you try to compress like a news article, the length of the news article is maybe a few hundred words or 1,000 words, but the alphabet size is 500,000. So this log n over n is small, maybe. This is 1,000, but k is 500,000, so this term is huge. Okay. So, so for large alphabets, if there's no limit on the alphabet sizes, in fact, it's going to be infinity. Otherwise, it can grow linearly with the alphabet. Okay. So, so again, so this is in some sense impossible. If you want to compress a sequence and the alphabet size is large, you'll incur a very high penalty. Again, impossible. Again, some number which is infinite. So again, what we believe is somewhat natural modification is looking at patterns. So every sequence, you can view it as a combination of a pattern and a dictionary. So for example, if this is your sequence, I am Sam, Sam I am, so it's a sequence of words, then the pattern is going to be the first word that you see, you call it number 1, and then number 2, number 3, and so on, and then I again is number 1, and M is number 2. So every time you see a word, you give it a number, and then you follow this numbering. Or here's so this is the pattern, and the dictionary says that 1 corresponds to I, 2 will correspond to M, and 3 will correspond to Sam. Or take this to be or not to be. What is the pattern? So 2 is 1, and B is number 2, right? And 3, 4, and then 1 and 2, right? So this is the pattern. Okay, in the dictionary, 1 is 2, 2 is B, and so on. Okay, so this is the pattern. And when you think about it, if you were going to compress a sequence of words, it's very natural to compress the pattern and the dictionary separately because the pattern follows the grammar of English, like which word will go after which word, and the dictionary that says that this word is SAM and this word is AM and so on. That follows the rules of like how words are, what is the probability distribution of structure of words in Russian. These are two different things, like which words should follow which other words, and what is that vowels should go after letters and so on. That's a different rule. So it's natural to compress the pattern and the dictionary separately. And you can also show that the pattern has essentially all the entropy, because if you look at a long sequence, then the, let's say ID, then the entropy of the pattern will grow linearly, because every time you get new word, it's a constant number of bits, constant entropy. On the other hand, the dictionary will saturate. Even if the dictionary is infinite, definitely if the dictionary is finite, it will saturate. But even if it's dictionary, new words go down. So the pattern is essentially all the entropy. So just like you define the redundancy of words or symbols, you can define the redundancy of patterns. It's exactly the same. The redundancy can be defined for any distribution. So here we're just looking at the redundancy for patterns, the same definition. We normalize by n. We look at the best compression algorithm. Like we look at the worst distribution and the expected. How many? If you knew the distribution, then you'd use the actual probability of the pattern. You don't know the distribution, you'll use your guessed probability of the pattern. So you guess this redundancy. This is how many bits you're wasting on the pattern, more than you need to. And what we have shown 10 years ago was that the redundancy of patterns does not depend on k. So beforehand, like for the actual sequences, the redundancy grew linearly with k. The redundancy of patterns is independent of k, again, uniform bound. There's some constant you put here, some constant put here. No dependence on the alphabet size. It always goes down like that. So there was a gap, and this is something that, like I mentioned, some of the other students. So actually, this is Jayadev actually showed that the lower bound is correct. So it's close that gap. So okay, so you can show that. I don't know if this is yes.
That's what I understand the situation.
Right.
So you are saying that if I need to compress a sequence, the redundancy is infinity.
And just to be precise, the redundancy, you can think of it as k minus 1 over 2 log n.
Yeah, it goes to infinity.
Correct. Yeah, that statement is correct.
But here, the redundancy of the pattern, which contains most of the entropy, is bounded, right?
Correct. Correct.
So that means that the dictionary takes little entropy, but the redundancy is very bad.
Very good observation. Correct. So the confusing thing when you first think about it is you think that something that has a lot of entropy will have also a lot of redundancy, but that is not true. Something can have a lot of entropy but zero redundancy, and something can have little redundancy, little entropy, but a lot of redundancy, like in this case.
I'm a little bit confused because the dictionary takes up so little entropy. Why don't just forget about dictionary? You just focus on the pattern in terms of the sequence.
Okay.
So then why would my redundancy be very bad then?
Okay. I'm not exactly sure what you mean, but here's the issue. Do you agree that the redundancy of the the entropy of the dictionary is small? Do you agree with the statement that most of the redundancy is with the pattern? And the reason, again, we're looking at IID sequences here. The redundancy of the pattern will grow linearly. Every time you get a symbol, then the pattern you need to say, is it 1, 2, or 3? You agree with that? And you also need to agree that the redundancy of the dictionary will saturate, because we learn, unfortunately, we learn fewer new things, fewer new words than these guys, right? Because we've seen it all, right? So the number of new are smaller and saturate. So it is a fact which you agree that the redundancy of the that the entropy of the dictionary will grow will be a small fraction. In fact, it's sublinear. You can show. Okay. So you could. Yeah, maybe if you want to make a connection, you could, but yeah, you can see that. Yeah, exactly. It's your point that yeah, after a while you don't see new things. Thank you. Yeah, thanks. Okay, but to see that the redundancy of the dictionary, we agree that the entropy of the dictionary is small, but now I want to show that the redundancy is very large. So think that you have a very large dictionary. Okay, then just specify the word. You say which. Let's say your dictionary is of size k. Okay, so to specify which one, you need log of k. So that's where you get like the entropy is small, but the redundancy is large, because the redundancy will grow with the alphabet size k. So that's, you see? Yeah, right. But the point is that the dictionary, even though I'm sorry, the pattern, even though the pattern has constant entropy per symbol, you can actually, and even though the pattern will grow, eventually the size of the pattern, like the number of numbers that you'll use, will grow unbounded, good, but still the redundancy is bounded no matter what the alphabet size. It's bounded by these numbers. Actually, it's 1 over n to the 2.
So you change the problem. You solve the problem.
Yeah,
You solve the original problem.
Correct.
The original problem cannot be solved.
Correct. Just like in the first case. Just like in the first case, we changed the problem. We solved the first original problem could not be solved. We changed it. We could solve it. Okay. All right. Okay. So summary for compression. If you want to compress ID sequences over k element alphabets, the redundancy is defined to be the number of bits beyond the entropy that you need when you don't know the underlying distribution P. And if you look at the sequence itself, then its redundancy is roughly k minus 1 over 2, k minus 1 over 2 n log n. So if k is fixed and n increases, it will go to 0. But if k is large, comparable to n, then you'll get something large. In fact, you'll get a constant. For large alphabets, the redundancy, if you look at k large, it will be infinity. And the natural modification is to separate the sequence into pattern and dictionary. The pattern has most of the entropy, and yet the pattern redundancy is 1 over n to the 2/3, so it does not depend on k at all. It's independent of the alphabet size, goes down to 0 at this rate. Okay, and independent of k, and therefore, if you look at k, which is infinity, then it's still going to be, doesn't matter, k does not matter, so it's 1 over n to the 2/3. So if you remember in the previous thing, we took something which was infinity and reduced it to a constant, right? Look at the L1 distance. I'm sorry, we look at the number of samples that you needed. From infinity, reduced to a constant. Here, in terms of redundancy, we take something which is infinity, and we reduce it to 0, actually. Because this number, as n increases, goes to 0. Okay? Right. Uniformly, there's no alphabet size. Okay, any questions? Okay, so, okay. Okay, and if you're looking at prediction with log loss, it's exactly the compression. It's exactly the same question, so you'll get the same thing. Okay. So, any questions about compression? Okay, so classification. Okay, so what is the classification part? You have we continue until what time? So we have an unknown discrete distribution, 2 unknown discrete distribution P and Q. And so classification is the problem. You're given some training data. You're told, okay, this is, these things are good, these things are bad, and now a new thing comes in, and you want to classify into good or bad. Okay. So you have 2 unknown discrete distributions P and Q, and you have a training set that consists of samples from P, n samples from P, and n samples from Q. And then you get a new sample, which is a test sample, which is distributed either according to P or according to Q, and for simplicity, we're going to assume equally likely. Okay, and the question is which of the P and Q generated Z. So that's the question. All right. So let's do an example. So suppose that P generated X, which is AAB, and Q generated Y, which is BCB. Okay. So intuitively speaking, if Z is A, so now Z turns out to be A, would you say that it was generated according to P or according to Q? P, very good. Do you have a chocolate for Professor Uber?
I can get one.
P, okay. Now, if you get B, then? Most likely you'll say, I need your help because, so we have got A, B, and then BCB, and now we got B, so what would you say? Yes?
You're asking me?
Yeah, of course.
So what is this? So what's going on? P generates...
So, okay, I agree with you. There are lots of, you're right, your question is very well placed. There are too many symbols.
Yeah, too many symbols.
So, okay. So just think this. You have training AAB, training BCB.
So I have what? AAB?
AAB is, I have one distribution, it generated AAB. I have another distribution, it generated BCB. And now I got A. Would you say generated by this? Is A closer to this one or closer to this one?
So why is P generating XQ?
Okay, so you told us yesterday that you don't like too many symbols, and we see that you're on it. Okay, no, that's good.
Yeah,
so I agree with you that for this examples I should not have shown this, but I will need to use these symbols later on, so that's why I'm introducing them. So just now concentrate. Forget this. I agree with you. There's extra information here, unneeded. I have one distribution generated AAB. I have another distribution generated BCB. Okay. Yeah. I think I need this. Okay. So, okay. What would be a good example of classification? You get, when you get spam mail, okay? Give me some examples of words that it contains, spam mail.
XXX.
Okay, very good. Okay, give me more. Okay, so it contains words like XXX. Maybe it contains like credit card or and so on. On that end, non-spam mail it will contain words like meeting. That may. But you get words like meeting and like grades and so on. Right. So so now now there's a new mail that comes in, and you look at, it consists maybe of a single word, and the word is meeting. Would you say it comes from the spam or from the non-spam? Say it from non-spam because it appeared many times in the non-spam mail. Okay. So here is this thing I get. So here I got 3 samples from one distribution. I got AAB. I got 3 samples from the other distribution, BCB. And now this new one I need to classify is A. So A appears more times here, so most people will say that it corresponds to AAB, which is P or X. Okay? And on the other hand, B, then maybe most people will say it's closer to BCB. Okay? So I'll classify it to BCB, which is Q or Y. And again, I'm using those extra letters because I'll need to use them later on. Okay. And C again will say from Y or from Q, and D will say either one because we have not seen it. Okay? All right, okay. So what are applications? So like we said, spam filtering or movie selection, like maybe Netflix, they know which movies you liked, they know which movies you did not like, so have a collection, and now they have a new movie, they want to see if they close to you or not. And they say, is it more like the movies that you liked, or more like the movies that you didn't like? Or medical diagnosis, you have all these people are sick, all these people are healthy, a new person come in, is this person sick or healthy? Stock recommendations, good stocks in the past, bad performance in the past, and so on. And so on. And we like to think that life is like that, because every decision we make, with things that worked out, things that did not work out, a new opportunity comes in, we say, oh, this is similar to this bad experience we had. Okay.
Is it IID?
Yeah. Yeah, everything is going to be IID. If I didn't write it, then I should have. Yeah, thanks. Thank you. Yeah, everything is IID. You can ask for all these things. You can ask, maybe this one is the list that we've looked at non-IID, but definitely for the other previous question, you should ask about non-IID. And for the first question, maybe it's okay. All right. So everything is.
Just an official question. When you say XN is P, you mean XN is IID P, is that right?
Correct. Yeah, I should have written IID. I forgot. Yes.
I'm just trying to explain why I
So,
was confused.
okay. So yeah. So XN is distributed according to PIID. Yeah, I apologize. Okay. Sorry. All right. Okay. So remember when we said when we do things information theoretically, we said one of the things we said was trying to do things as best as possible. Okay. So in the case of compression, we're lucky because we know what the best possible thing. The best possible thing that everyone here told me was entropy. Right? If you want to compress, the best thing to do is entropy. The question is, how close can you get to entropy? Okay. Here, unfortunately, there's no such answer. If I give you P and Q, there's no entropy. There's no one number that is the number that you're trying to reach. But still, you want to do as best as you can. Okay. So even though you don't have a formula for this. Okay. So the best, you can think that maybe the best thing to do is the omniscient classifier, the classifier that knows everything. Okay? So this is a classifier that knows P and Q in advance. Okay? So you can think of a classifier that knows P and Q, and now comes Z and wants to say is Z generated by P or generated by Q. Okay? Once you're looking at a classifier that knows P and Q in advance, the problem becomes that of hypothesis testing. You know what P is, you know what Q is, and Z is given to you, was Z generated by P or generated by Q? It's just a simple hypothesis testing question. And that classifier, of course, does not even need to look at Xn and Y, because the only purpose of Xn and Y is to learn the distributions. But here you know them already, so they'll just confuse you if you look at them. So, okay. So what will this classifier do? So I have two distributions that I know, P and Q. I know P and I know Q, and I get a sample Z. And I'm asked, according to P or according to Q, what should I do? The one that gives it the higher probability, right? That's clear, right? So this omniscient classifier classifies the distribution that assigns to it the higher probability. In other words, if P of Z is bigger than Q of Z, then you classify to P. Otherwise, you classify to Q. Okay? But of course, the drawback, I should have done it in red, is this classifier has a problem, which is it's required to know P and Q in advance. So it can do this rule, right? If it doesn't know P and Q in advance, it cannot do this. Okay? So that means that for every P and Q, you need a different classifier. And of course, you don't know. You just build a classifier. You don't know what P and Q is. You first design a classifier, then you're given P and Q. So you cannot do this. So this is impossible. This is, again, an example of impossible. You cannot achieve this. You cannot do this You cannot do this in real life, only if you're God. Okay. So let E star PQ be the error of this omniscient classifier for P and Q. And then again, remember that it requires knowing P and Q in advance, and therefore is impossible. But if you knew it, that will be the error. Okay? And the question is, can we design a classifier, just like for the case of compression? We want to design a compression scheme that will achieve the performance of a person who knew the distribution in advance, in other words, the entropy. Okay, so the question is, can a realistic classifier, namely one that does not know P and Q in advance, can it approach this E star, this best error? Okay. So this is.
In what sense?
So I'll define it. But very basically, we want to say if the number of samples is n, we want to be close to the best error that you can get. Okay, so we want, in other words, we want a classifier that performs nearly as well as the omniscient classifier. And again, E star is the lowest error of any classifier for PQ, and it's achieved by one that knows P and Q in advance. If your classifier is C, then its error will depend on n. The more training samples you get, the lower the error. So the omniscient classifier, there is no n because it doesn't even look at the samples. But your classifier, its performance will improve as you get more and more samples. So it's the error of your classifier C for P and Q with n samples. And we find the degradation of C with n samples to be the lower increase in error. So if your classifier is C with n samples, its degradation is the maximum of all possible pairs of distribution of your error minus the best error. So by how much worse are you than the omniscient classifier for any pairs of distribution? Is that clear?
So this is the error probability, right?
Correct. So E is the error probability, namely, I generate a sequence according to P, I generate a sequence according to Q, and then I get Z. My classifier will do some classification. P and Q, it will incur some error. There's some error probability. The omniscient classifier will just assign to the distribution gives Z the higher probability. It will also have an error. And the difference between them is this.
Does it matter whether I take the difference or the ratio?
We looked at the difference. The ratio will be more sensitive because if you take the difference, both of them are like, say, the error is always less than 0.5 because you can always flip a coin. But if the errors are close to 0.5, then the ratio is very close to the difference. But if the error is close to 0, then the ratio is higher. So we're not that sensitive. We're looking at just.
Because usually we're interested in full error probability, full error probability in one scale, which means the ratio is more relevant. That's
a good point. We looked at the difference. I think that maybe definitely if you look in compression, you tend to look at like the KL divergence. For these problems, I'm not sure. If people say, you want to classify in my classifier, this classifier has make this error, this classifier. I can guarantee you that my error is at most 0.001. Maybe it's sufficient. But I agree with you that looking at the ratio will be a more sensitive way of doing it. I'm not sure.
The error is the expected value of all the samples that expire.
Correct.
Not mentioned disease, but also.
Yeah, correct. It's a probability. So one way to say is the expectation. The other one is just the probability. You have a rule. Maybe your rule is such that you see appeared more times in this thing.
But the rule itself will be probably correct because the samples you get is already functional X.
Right. So I would think that the rule I'm thinking of describing the rule in the deterministic way. For example, assign to the training where the test appeared more times, that deterministic. But then you're right. Given the samples, given the training and the test, will get a random thing, and you're looking at the probability that you misclassified.
The rule is a function of the random
data. The rule is, because both of you are saying the same thing, the rule is a function of the data. And I think that the best rule will be a deterministic function of the data, but because the data is random, the rule will be random. Okay.
The rule is not random.
Yeah, perfect. So we agree. Yeah, that we agree. Yeah, you have a deterministic function, but then you could, and then you apply to random data. Okay, very good. Okay.
But there is a question of whether you allow randomized groups.
That's right, but I think that the best thing to do is not allow it. But all these things will not matter for what we say. If you want, you can do a randomized roll. It will not matter. Okay. Okay. So this is for your classifier C, and obviously you'll want to choose a classifier that has the minimum degradation. So we define Dn to be the minimum of all classifiers of the degradation. So someone had like the best classifier possible, and that's Dn. So you have Dn of C because your classifier was something, and Dn is the best, the degradation of the best classifier. Okay, so the question is, so it's the lowest guaranteeable increase in error with n samples. Now, notice that the worst possible increase is half because the E star, the error is at least 0. And you can always guess, random guess half. So you can always achieve Dn, which is a half. By just guessing, you're making an error half. The best is 0, maybe. So you're off by half. So here we're not going to start with infinity. We're starting half. Half is our new infinity. Okay, so therefore Dn is always less than or equal to half. And the question is, can you come up with a classifier such that if n is 1,000,000, then you have less than half, let's say 0.49. Is there a classifier such that with 1,000,000 samples, you're guaranteed that your error is less than 0.49? Is there such a classifier? So is some classifier always 0.49 away from optimal? And when I say always, is for n, let's say, I should have written this a little better. For n, let's say 1,000,000 something, for any distribution, pairs of distribution will be 0.49. Can you find something like that? Okay. So the first thing to show is no. This is the impossible. That Dn is half. You cannot come up with any with a classifier, even with n like 1,000,000,000. Its degradation will be less than a half. Will be 0.49. So let's show that. So given any n, we want to show that for every n, your degradation could be as high as a half. So if your n is 1,000,000,000, still you can find examples where your degradation is a half. So take k, which you remember is the alphabet size, to be 4 times n. So choose n as large as you want, 1,000,000,000. Okay. Once you choose n to be large, we'll choose k to be even larger. Clearly, if you fix k in advance, k is the alphabet is size 2, then eventually you learn. The trick is to show that if you don't have a bound on k, then you can make large errors. So take k to be 4 times n, and let p and q be uniform over this joint subset of size k over 2 of this set. So for example, maybe p is uniform over the first half element, and q is uniform over the second half element. Okay. Or p is uniform over the even numbers, and q is uniform over the odd numbers. So we're looking at p and q that has disjoint. Each of them is over half the elements. Each of them is uniform. Simple. Okay. So here is an example. So k is 20. Okay, so I'm sorry. And let's say we took 5 samples. So k is going to be 4 times that, which is 20. And then p and q uniform over 10 elements. So see here, p is blue, is uniform over 10, as q is uniform over 10, and they're disjoint. Okay. So the first question is, for this p and q, if you look at E star, so what is E star for these two p and q? 0, right? So should we give people chocolates like preemptively or something? So yeah. I think I know I need it, so I'm sure that you guys need it too. It's an encouragement to respond. Yeah, you can have everything. So okay. So what is E star again? I know a couple of people said. Now with the advantage of having chocolate coming up, 0 and 1. Disjoint. So if you know the two distributions, you know what are the blue, what is P and what is Q, and you get a test thing, you see if it's blue, you know which one it is. Okay. So E star is 0. How many samples do you need to get 0? How many training samples do you need to get that if you know P and Q? Training. 0. right? Because you know P and Q in advance. So it's for any n, even n equals 0. Okay. On the other hand, what is EC? Let's say you try to come up with a classifier, but you don't know P and Q in advance. Okay. So observe that because n is k over 4, right? We chose k to be 4 times n, so n is k over 4. That means that the probability that z does not appear in anything that you have seen, does not appear in either the x training or the y training, what is it? Is at least 1/2, right? So it's at least 1/2, right? Because why? Because here you're taking 5 samples, okay? So each one will give you, this is the first sample, will give you 2, second one 2, and so on. Each one gives you 1 blue and 1 red. And after 5 samples, you'll see 10 elements, right? So you have k over 4. You have k over 4 samples. Each one you get x and y, so you get k over 2. So at least half of them you have not seen. So the probability that z has not appeared in either x or y is at least 1/2. And so your error, and that implies that your error is going to be, in the case that it did not appear, which is 1/2, you need to make a guess, and then you make an error of 1/4. So your error is at least 1/4 for any estimator. Okay. So this shows that your loss is your degradation is at least 1/4. Okay. But like I think maybe Rudiger said before, for a different example, if here we took k, which is 4n, if we took k to be n square, then this 1/2 will be close to 1, as close as you want to 1, the probability that you have not seen, right? The probability that you have not seen z can be as close to 1 by taking the alphabet size to be sufficiently large. So this dn will become 1/2. So this shows that you have no chance of uniformly approaching the error of the best classifier. So this is the impossible part. Okay. So this.
It's obvious, right?
Yeah, it's kind of obvious. Yeah. All these examples that I'm showing you, I think, are kind of obvious. The alphabet size going up linearly with k, kind of obvious.
Substantial fraction.
Right. I agree. So the obvious part, and I agree, is that to perform all the questions that we're asking is, we believe that you're given some number n. N is not infinity. The number of samples is not infinity. The number of samples given is given to you is 1,000. What can you say? What can you guarantee? Okay. So if the alphabet's, if your alphabet's small, then you're in luck. But if your alphabet is large, like you said, then you're not luck. And what we're trying to do is we're trying to look at these problems that are impossible with large alphabet and modify them to get something which is possible. All right. So what we want to talk about is our label invariant classifiers. So what are they? So remember that E star requires knowing P and Q in advance, and that gives E star gives it too much power. You need to know something that normal people don't have. No real classifier knows that much. So we're going to look at what we think is a natural modification, which is we're going to compare it not with this classifier that knows everything. We'll compare it still with a classifier that knows more than humans do, but not as much. We're comparing with a classifier that's a little more realistic, and classifier that is label invariant, and it's sometimes called canonical classifier because it's so natural, actually. Okay, so here's an example. So suppose x is AAB, and y is CBA, and this is z is A. Okay, and so you'll classify z somehow. Okay. Now here I have another sample. So x is now UUV, y is WVU, and z is U. What can you say? Can you tell me something about how you'll classify U? Yeah. So I cannot tell you whether I'll classify to x or to y. That depends on what you do, right? Most people will classify to x, but maybe some people won't, right? I don't know, for some reason. But I don't know what you'll do, but what I can tell you is that you'll classify U the same way you classify A, because what we did was, here we took a label invariant, we changed every A to U, here, here, and here. We changed every B to V here and here, and we changed every C to W. It happened to appear only once. So the issue is that if you take both X, Y, all X, Y, and Z, and you consistently modify, relabel them, both in X, Y, and Z, the conclusions should stay the same. So that's a label invariant classifier. If you relabel everything the same way, if this were classification of animals and this was a classification of cars, the new classification should be the same. or if this was better, if this was your classification in English and this is your classification in Chinese, they should be the same. The fact that you're using here English and using your Chinese renaming should not make a difference. So these are what's called label invariant or canonical classifiers. Okay. So classification in both cases are the same. And in other words, if you do consistent relabeling of all triple, you're not just changing one, you're changing all of them, then you should end up with the same classification.
What are you writing randomized classifiers here or?
Again, it's the same as we were saying before.
The question I'm asking is, see something that you have not seen before. Suppose see something you have not seen before, and you force all the things that you have seen before to fall into one set. But then you might so. Because the say labeling variant means that whatever if I replace Z with something else I haven't seen before, then you put the same set. But maybe it's
okay. Sure. So let me be a little more maybe general. And whatever the rule is that you're applying, so if you've seen AB, if you've seen this, you're going to use some rule. Okay. Then if you see this thing, you should be using the same rule. If your rule was deterministic, it should be deterministic. If your rule is randomized, it should be the same randomization, the same probability.
Yes. The question was whether you want to make it even, whether you want to make it equally like the X and Y or.
Yeah. The only point what I'm trying to say is that your classifier should use the same rule in these two cases. So because we assume no prior knowledge, all natural classifiers are canonical. Okay. And what we can do is we can make E star tilde, I'm sorry, be the error of the omniscient label invariant classifier. So we're not allowing all classifiers. We insist that the omniscient classifier is label invariant. It doesn't look like a big restriction because it's very natural, but we're going to make this restriction. It looks like we almost no restriction, right? We insist that the classifier that we compete with should be label invariant. And like I said, we don't think of it as a big restriction because all classifiers should.
But that would limit the omniscient.
Correct. So now that's right. So this classifier knows P and Q, still knows P and Q, but it's restricted to be label invariant.
If you just use the natural, probably not be.
Okay, so two answers. Number one, I 100% agree with you. Classifier has to be label invariant. There's making classifier that's non-label invariant makes no sense. I agree with you on that. But when we compare, when we compare to the omniscient classifier, you can think of a classifier that knows the actual distribution. We can look at if the value is 5, it will do one thing. And you see, like for example, things like going back to what Chandra was asking. If something that you have not seen before, if Z is something you've not seen before, if the classifier knows the two distribution, it will may assign depending on what Z is. So think Z, the testing has not been seen before. So, that's right. So if the classifier is as before, omniscient as before, it could look at the value of Z and say if Z is A, then I'm going to assign to P. If Z is B, I'm going to assign Q and so on. Now we're not allowing that because we say if you have not seen it before, it has to be the same rule. That's follows.
You're forcing your classifier to depend on the data.
Correct.
Whereas the omniscient classifier you said earlier.
Right.
That's not dependent.
That's right.
So you rule out
Right.
that classifier.
So the previous classifier was omniscient and omnipotent. It knew everything and could do anything. Now the new classifier is omniscient. It knows anything, but it's not omnipotent. We're forcing it to be a little more realistic, to be a little more like what we think are the natural.
So it might be more. But it's not very human in the sense that, for example, let's say that the labels are like skin color, right? So humans naturally have this side information that says, oh, if this person, like let's say, okay, I'm being, this sensitive politically here, but let's say you're in the US and your skin color is black, you're likelier to be a criminal, right? So in some sense, you're taking some side information which exists from outside a model, and then you're using that to classify.
Right. So example, notwithstanding, we're assuming that all the information you have is here. If you want to introduce, you say you have additional information, then that's fine. Incorporate it into some other thing that you're given, and then do it label invariant on that, right? But we're not assuming that this is all the data you have. Otherwise, you have more training data incorporated. Okay. Are we okay? Everyone is okay? Yeah. All right. Okay. So now E star tilde as opposed to E star tilde is the error of the omission label invariant classifier. So you're forcing it to be label invariant, but you're still allowing it to know the distribution in advance. So it also requires, to get this E star, you also require prior knowledge about P and Q. Okay, and we'll define D and tilde to be the degradation of the best label invariant classifier relative to E star. So we want our classifier again to be also to be label invariant, but we're comparing now label invariant to label invariant. Okay, is that clear? So that's the modification that hopefully will take it from impossible to possible.
I still don't get like what are you choosing as the you're comparing it to something, but is that what is that?
So okay, so in this case had the advantage that the best one was obvious. If I knew P and Q, then I would assign it to the Z to the distribution that gives it a higher probability. Okay. In this case now it's a little more difficult to see what it should do. So now you know, you can think there were two ways of looking at this omission classifier, this new omission classifier. One is to say that it knows the distribution, but is forced to make a decision that is label invariant, a rule that is label invariant. That's one way. That's the way I described it. Another way to describe this classifier is to say that you're not given the distribution, but you're given. So what is the distribution? The distribution consists of a matrix, which is 2 by k, right? There's P1 up to Pk and Q1 up to Qk. So that's the two distributions, right? Another way, so that the omission classifier, the original one, knew this 2 by k matrix, P1 up to Pk and Q1 up to Qk, and then make the decision. This new classifier, another way to look at it, is to say that it knows this matrix, but without the labels. It knows that for one element there's one probability 0.9, 0.1, for another element there's probability 0.05, 0.3. It knows this pairing, but it doesn't know the labeling, and now it needs to make a decision. So if you look at this interpretation, then you can also come up with a rule for this classifier as well. Look at kind of the pattern. So for every two distributions, P and Q, we'll look at the error of the best label invariant classifier. That gives us E star. And we want to come up with an estimate that does not know P and Q and approaches E star. Okay. Okay. Are we good? Are we clear or not so clear?
I mean, for some simple examples, can you actually work out what this?
Yeah. So I was saying that okay. So in order to do that, you need to look at a different definition, an equivalent definition to the one written here. The one written here says that so first of all, you agree that the information that you know about P and Q is you're given a 2 by K matrix, right? For P, you're given all the values, and for Q, you're given all the values, and you have the correspondences so that when you see Z, you see if in that column, P is bigger than Q, Q is bigger than P. That's the original one. Okay. For the new classifier, an equivalent way so you can say it like this, you know the matrix, but your rule has to be label invariant. So that's one way to say it. Another way to say it, because the label invariance, you can say that you're given the matrix, but you're not given the labels on top. So you're not saying that this is A, this is B, this is C, this is D. You're just saying for one value, P assigns probability 0.8, Q assigns probability 0.1. For another value, P assigns 0.1, Q assigns 0.5, and so on. And you're given this matrix, but without the label. Okay. Now you're given, so you'll be given now n samples from P and n samples from Q. Okay. And then you'll be given Z. Okay? What you could do, it's a little more difficult, but you can calculate now. They probably assume that everything is uniform. All possible permutations, k factorial permutations, are equally likely. And you can calculate the probability that you will see one element. It's like a two-dimensional pattern. So you'll see, so every time you get one, your pattern will be 1, 1, 1, 2, and so on. And then you'll get Z. And you calculate the probability of that pattern. You'll get a probability of this under the assumption that Z is generated by P and under the assumption it's generated by Q, and you see which one gives it the higher probability. So doing the example will be a little complicated because you need to look at all possible permutation. Does that make sense? Okay. All right. So, all right. So, so we know that dn is equal to half, and that's the impossible thing. And the question is whether dn tilde could be smaller than half. So first, let's look at the empirical frequency classifier. And so, okay, so what is the empirical frequency classifier? It just looks at the which training data had more of the test. Okay, so let's say the x was a square AAB and y was CBA, and z is a. Which one would you classify? X. Thank you. Okay. And let's say you got ABAC and CBAC, and you got C. Which one would you classify? Y. And so the question is whether this is there anything better that you can do? So everything, there's no more information that you have, right? I mean, this is all the information you have, right? And you see A appearing more times here, so we say here, C appearing more times here. Is there anything better you can do?
What happens if I have not observed?
Then half maybe or something like that. I don't know. But let's say you observed. Anything better you can do? Like, would you? So here there's some distribution that generated A twice, and this one generated once. Would you ever say that this one is more likely to generate A? So what the empirical frequency classifier does is it assigns to the training with more Z, assigns Z to the training that has Z more. In other words, it's a proxy for the distribution that assigns to Z. Remember, what we want to do is we want to choose the distribution that assigns to Z the higher probability. If P...
Suppose if P had support on Q, and Q had support on high level, but you know that on Q you had higher probability for A. Okay, on Q the
so let me no. Let me say right.
I can infer something from this.
So yeah, that's right. So if you it's right. Okay. So should we ever do something different?
Does it depend on how much diversity are there in the other?
It's up to you. You can decide.
You can just use your distribution.
Right. So one thing to observe is that the empirical frequency classifier is label invariant, right? Clearly, if I change consistently the labels here, it will still classify to X and so on. So it is label invariant. That's fine. That's not a problem. Okay. So it seems that it's clearly optimal, right? But why, right? Especially since I'm making such a big fuss, like you may wonder why, right? It's not, why should it be optimal? But what I want to show you that it's actually not optimal. I want to show that it's not competitive, definitely not with the omniscient one, but also with label invariant classifiers. Okay, so I want to show you low bound on that. If you look at the empirical frequency classifier, I want to show you that it has a degradation compared to classifier, so it's not optimal. So it has a degradation compared to the best label invariant classifier. So take two very simple distributions. P is uniform from 1 up to n, and Q is uniform from 1 up to 2n. So very simple. So what is the optimal classifier does? So first of all, let's look at the optimal classifier that's not restricted to do anything. So it can do anything it wants. It doesn't have to be label invariant. Okay. So we know that what it will do is it will see if P of Z is bigger than QZ, then it will assign it to P. Otherwise, it will assign it to Q. Okay. In other words, so remember that X is distributed according to P and Y according to Q, and we let NZ, Z is what you observe with XN, be the number of times that Z appeared in XN. So just NZ is the number of times Z appears in XN. Okay. So if NZ of Xn is bigger than or equal to 1, that means that Z appeared in Xn, then what can you say about P of Z? So if Z appeared in Xn, okay, then xn is generated according to p, and remember p is uniform 1 up to n, that means the p of z is 1 over n, right? Because p is uniform 1 over n, x is generated according to p. Okay, so if z appeared in x, then that means that p of z, that means that x is that z is here, and z is here. Its probability is 1 over n. Okay. On the other hand, if z appeared in yn, if nz of yn is bigger than 1, if z appeared in yn, that means that q of z is what? Because y is generated, again, y is generated according to q, and q assigned to everything probability is 1 over 2n, so its probability is 1 over 2n. And therefore, the omission classifier, the one that's not restricted to be labeled invariant, if z appears in both training sets, it better assigns it to p, to the distribution that's generated by 1 up to n. So I have distribution 1 up to n, I get some samples. I have distribution 1 up to 2n, get some samples. And then z. If z appeared in both of them, then the omniscient classifier that knows the distributions will assign it to the smaller distribution, the 1 up to n. Okay? And one nice thing to observe is that this classifier is also labeled invariant. It just says that if it appears in both of them, then assign to this one. Okay. Okay. Now, but let's look at the distribution of how many times z appears in xn. Okay. So this is z is some number between 1 and n. Okay. And xn is some n samples. So the number of times that z will appear, z is the test, and x is n samples from this distribution. The number of times that z will appear there is binomial n 1 over n, right? Because I look at z, whatever number it was, and now I look at the sequence x, n samples according to this distribution. Each one is probably 1 over n of being z. So it's binomial n 1 over n, which is roughly Poisson 1. Okay. On the other hand, if I look at the distribution of z, number of times z appears in yn, it's binomial n and 1 over 2n, right? Because z is some number, and y is generated from 2n numbers. So the probability that z will appear in the first time is 1 over 2n, 1 over 2n. So it's binomial this, which is Poisson 1/2. Okay. So now, so ideally, we would like to classify to the Poisson 1 because it's more likely. But there's some probability that if we do empirical frequency, there's some probability that that this distribution, the Poisson 0.5, will give a larger number than the Poisson 1. And in that case, we make a mistake. So in other words, here, if we look at what we should be doing, is we should look at z. If it appeared in both of them, we should assign to the smaller distribution. But if we look at them, if we look at empirical frequency, then we'll see which one appeared more, and there's some chance that this decision will be reversed. Okay, so this happens probably 0.03. So your additional error will be at least 0.015. Because in this case, we know what you should do. We know if they only appear in one, then it's kind of clear what to do. But in this case, you know what you should do, and there's some chance you'll be doing the reverse. Right. So in this case, we classify to y, namely to this distribution, instead of to x and the p. Okay, so we're making an additional error. So this classifier is not optimal. So additional error is 0.015. Because what we show, okay, so the good question, because the error of the classifier, you can say it's the error of, when you calculate the error of classification error, you can look at the condition on every two symbols that appear. It's the probability that two symbols appear, and then the probability that you make an error on those, right? So it's summation of all these things. And for every combination of symbols for x, y, and z, you should be making the optimal decision. And what we're showing here is a range of X, Y, and Z for which you're not making the right decision. So for everything else, you'll be adding to it. So your classification error, you can, when you calculate it, it's the probability that you make a mistake when X and Y are this, and you make a mistake in X and Y are this, and so on. And we show the range where when Z appears in both of them, and for this you're not making the best decision. And you.
In fact, the omniscient classifier you wrote here is implementable, right?
Correct.
It doesn't really require PNQ, actually.
Yes, but in order to derive it, you'll need to know what P and Q. Otherwise, if P and Q were not like that, then you would not be using this classifier. So, right? It's because these are P and Q that you're using this classifier that if it appears in both, you assign to one. It is like it is labeled. It happens to be labeled invariant, which is why we can compare to it.
The other thing is if you join, it's the actual program condition problem.
Correct.
X appearing on it. So that's why you're adding on to it.
Correct. Okay. So this shows that this classifier is not, the empirical frequency classifier is not optimal. And I know it's maybe a little surprising, but remember going back to, like someone was saying, the good Turing estimate. The good Turing doesn't just look at the empirical frequency, it modifies it. And it can modify things that something appeared fewer times, you'll give it higher probability than something that will appear more times. Because you're multiplying by this, the ratios, by this ratio. So you can change those probabilities. Okay. So, so this shows that the empirical frequency classifier is not competitive. However, okay, so remember that if you looked at classifiers that are not necessarily label invariant, then the biggest degradation is 0.5. And we asked whether for label invariant classifier the degradation is less than 0.5. And you can relate classification to estimation over sequence pairs. So now you need to estimate 2 sequences instead of 1. And modified new estimators that we had to sequence pairs. And then you can get a classifier such that its error is at most 1 over n to the 1/5. And that's so it approaches the performance of the omniscient label invariant classifier. It's uniform over all k. Again, k does not come in. And this can be classified in linear time. And we think it's the first uniformly competitive classifier. So basically what we did was we modified the definition of competitiveness, so to make it possible. And we have a low bound, which is 1 over n to the 1/3, so there's a gap between them.
So your definition is new, and by definition it must be first.
Yeah, so that's why I wrote to our knowledge that maybe other people have looked at it, or maybe other people have looked at a different variation, you know, so. Okay, so is that clear? So we're actually very close to the end, even though it says 47 here. So here is a test, because it's a school, two questions. Question 1. So this says that you can approach the performance of the best classifier for any distribution, right? That's our definition. That means that if you give me n, which is, say, whatever it is, then this is going to be a degradation regardless of the 2 distributions. So, but remember that we looked at the example with the disjoint support, and then we said, oh no, the error should be close to 1. That was the first example we had. If you have 2 disjoint supports, then if you know the distribution, you make no error. If you don't know the distribution, then we said you can make an error that's close to 1. So how come this does not contradict this result? Right, because the example that we had, we said you know the distribution, you know P and Q, you know the disjoint, you observe the sample, and you can say it belongs to P and Q. That's highly labeled variant. You know what the value is, you assign to P. This value P, this value Q is very labeled invariant. So we're not allowing this by insisting it's going to be labeled invariant. Okay, so that's one question. And the second question, even was going even further back. What is K? Excellent. Okay, very good. I think you've earned your lunch. So, just before that, just show you a couple of experiments. So just one slide of experiments. So first, I want to adjust the expectation. So don't expect, I'm going to show you the performance of empirical frequency classifier, which, because maybe it's hard to believe based on the example that, you know, it does better or something, maybe you don't quite see. So I want to show you like experimentation. But don't expect us to reduce the error from, you know, 50% error or something to 1%, okay? Because if that was the case, if one could reduce from 50 to 1%, number one, this would have been found before, if it was that big of a difference. And number two, if it was not found before and we found it before, we would not be telling you about it. We'd be starting a company, okay? So don't expect such a big difference, okay? In fact, so you cannot expect to halve the error. For example, the Netflix challenge that many of you may know about that they had a few years ago, they wanted to improve their recommendation system, and they had a measure for the recommendation system, so they could see what people have done. And what they said, they were giving $1 million for the people who came up with the best classifier. But if someone reduced the error by 10%, then the competition would stop right there. You don't even continue to the end. If you get 10%, you get the prize. Okay, so 10% reduction, they consider to be sufficient for them to just stop the competition right now. Okay. All right. So again, we took ZIF distribution. So there are two of them. One is proportional to 1 over I. The other one is proportional to 1 over I to the 1.5. And again, the alphabet size is 100. And what we'll see is a graph of the error versus the training length n for empirical and for the proposed classifier. Okay. And so here it is. So this is the number. This is the training length n, and this is the error probability of classification. As you expect, as the number of training sample increases, your error should go down. So this is empirical. It goes down from here to here, and this is the proposed classifier. It goes down like that, and you can see that, for example, if you take n equals 50 here samples, then your error goes from maybe 0.43, 43%, something like that, to something like 39%. So 10%.
Why does it not improve much when you?
Because remember, this is one curious thing about what we're doing. Z, the test is a single sample. Is a single sample. So even if you knew the two distributions, you will have an error. Because imagine that you see, like, it's not that you took 100 samples, but you took one sample. So you know one gives it probability 0.3, then one gives probability 0.4. You assign to 0.3, but there's some constant probability that you make a mistake. So for this, it will not go to 0.
So what is it?
So you can calculate it, right? I mean, if I give it for this distribution, I'm not sure. I'm not sure. Very easy to calculate.
So did you get the prize?
No. I think we're very far from getting the prize. Maybe the prize we get is lunch. I think that's the prize we're getting for going that far. I think this is the end. So summary. Any questions before we summarize? Okay. So we talked about 3 statistical learning problems over large domains. For all of them, we approach them from the out of the doable point of view. First one was sample complexity of estimation. And the results, let's say, are for KL divergence, but you can do them for L1 distance. So if you want to estimate a distribution of size k, then you need roughly k over delta. And in the worst case of all k, you need infinity. But if you look at total probability estimation, then the number of samples you need goes to 1 over delta square, okay, and which is no k in it. And for compression, redundancy, or log-log prediction, those two are the same problem. Then the redundancy grows linearly with k, and in the worst case is infinity. But if you partition into pattern dictionary and compress the patterns that have most of the entropy, then the redundancy of the pattern, regardless of the alphabet size, is something that goes down to 0 uniformly in n, no matter what the alphabet size is. And for the gradation of classification error, then if you compare to a classifier that can do anything, then your difference could be half. But if you look at label invariant classifiers, then your difference is at most 1 over n to the 1.5, and there's also a lower bound. I'm not sure if I wrote it here. Okay, and the point here is, in all of those, is that you can take a natural multiplication, take something that's arbitrarily bad to something that's arbitrarily good, And it shows you that you can do something. Like if this case, you might say, okay, there's nothing I can do. No point in even trying. But like here, you can see that you can do something that will approach. You can see you can compare yourself to how close you are to the best thing you can do. And we saw at least in one example here that when you do that, it actually also applies to the original problem, not the modified one. Okay, so it motivates and then it motivates solutions and allows you to do them and measure the new solutions and so on. And obviously there are many. If you can reduce, you know that if you can reduce something from infinity to 0, you know that there will be many other problems beyond that. Right? So many remaining problems. Okay, so I think. Oh, and if you want to read, you can look at these papers and so on. I think this is it. Oh, so okay. So as you know, this talk was going to be 2 parts. So this was the end of the first part. We just finished, okay? And the second one was to be continued, but I guess we'll, you know, summer school too. Cool. Thanks.
We've had a large number of questions from a small sample size. Now I wonder if there are other questions from anyone else.
There's someone in there.
What is the
So easier to first understand the probability estimator. So if you can do probability estimation well, you can do classification well. You can show that, right? I mean, that's the essence, right? You're trying to learn the distribution so that you can assign to the distribution that gives the Z a higher probability. So you need to learn the distribution well. So you need to understand the classification. I'm sorry, the probability estimation algorithm for the first part, and which I described to you the first step, which is the good Turing. Let's describe that. And then once you do that, you need to learn distribution over. Instead of learning a P1 up to Pk, you need to learn this matrix, which is 2 by k. That's what you're trying to learn. So it's an extension of this algorithm. So you're given now, instead of giving a collection of samples, you're given a collection of pairs of samples, and you try to learn this 2 by k matrix that will give a high probability to what you've observed.
And you have lower bounds showing that joint estimation is not necessarily too much better than this.
No, you need to do joint estimation. Definitely need to do joint estimation. The difference is that we don't have a tight lower bound for this one. We don't. Yeah, that's right. Yeah. But you do need to learn them together. Sorry. So there's this gap.
Oh, I see. Okay.
Yes.
My question is, what is the advantage of the information theory-based learning compared with the machine learning-based classification?
I think they're different. You know, like you can take many different approaches to this problem. It's an important problem. We're trying to understand, number one, the fundamentals. We're trying to see what is the best that you can do. For example, for many of these things, like even the learning, there were no lower bounds. So like maybe people knew that you know, you can do good Turing, you can learn it at some rate. In that case, well, infinity doesn't matter, but they did not have a lower bound on how well you can do. So you can ask what is the best you can do, and these information theoretic methods. And if we're going to continue to the second part, you would have seen them more. They give you a way to give you a lower bound. Also, I think that you know, like this approach of trying to do things competitively or universally, you know, is part of information theory. We're used to doing it for universal compression. I think it's interesting. Now, of course, people do really interesting things from all different areas, right? So I'm sure that there are reasons to do things in different ways, but I think what this shows is the information theory can contribute to this important question and show something interesting.
Other questions from the audience?
Yes. What about cluster? Is there any results in cluster?
We don't have results like this, you know, like out of the durable results for clustering. But the second part was going to be about estimating Gaussian mixtures in high dimensions. And for that, part of what we do is clustering. It is not of this nature, though, that something you can do, cannot do, but you need to do clustering and apply it. But it's a good question, whether one could define a problem.